Drilling down into that iceberg parquet layers, this is something that you've probably seen if you visited the iceberg documentation site. This comes up fairly often. Basically, this is kind of how iceberg works under the covers, and we'll go into more details what this looks like. So the top layer is the catalog, as I mentioned in the previous slide. It really holds a pointer. Right? In Hive world, the catalog has a lot more meaning. It holds a lot more information, like the schemas and the partitions and a bunch of other stuff. And if the catalog doesn't exist or can't hold all of your columns or all of your partitions, right? Think tens and hundreds of thousands of partitions over years, then the catalog becomes slower and slower and slower. In this case, we're sort of removing that dependency on the catalog, and we're saying, catalog, don't do anything. Just point me to where the iceberg table is, and iceberg will do the rest. So in this case, that's where this is. This is the current state of the table, right? This is the current snapshot. And then once that current snapshot is found, it points to a particular manifest file. And this is a list, a manifest file that lists additional manifests, right? So it says, I'm the snapshot, I'm the current point in time, and I'm going to give you a pointer or a link to a bunch of other manifest files. And those manifest files will give you more information about the specific physical files, right, that are actually holding the data. And this is kind of the two layers, the manifest list and the manifest file. So by using these snapshot in the metadata layer, the metadata files, we actually have this concept of snapshot isolation. I'll get into more details in a little bit. But basically, this lets you have concurrent reads and writes without stepping over each other. So like one user can read current snapshot and just read the data and do analysis on it, while another system is creating a new snapshot because it's updating or inserting new data into it. So that's the snapshot isolation part of it. We'll get into more details. The next one is optimistic concurrency locking. So now that we have these manifest files, the iceberg layer or the engine who's using iceberg can say, okay, I'm going to take the current snapshot of my data and I'm going to work on this. I'm going to make changes. I'm going to add files, remove files, whatever. Now I'm updating a copy of my manifest list and my manifest files and my physical files. Once I'm done making those changes in isolation, I then commit those changes to the table. And we'll talk about conflict resolution in a second. And then once you kind of do that over and over again, you have multiple systems of reading and writing. You also have automatic retries. So if you try to commit some changes, but somebody else is also making changes at the same time, you kind of fail, and then you retry the same thing again. So there's one question that came up, I think, on a previous slide, like how does Cloud IAM works within the architecture? Generally, Cloud IAM works within the architecture in the sense of you define object level permissions, which systems can access the data, and then you define catalog level permissions to say which user can access which schema entities on top. And then the rest of it is Spark or whatever engine you're using will have to have IAM permissions to the bucket, to the catalog, to those entities. Okay, sorry for that detour. Okay, last one is kind of the durable writes. So once you defined, you have a snapshot, you have the manifest underneath it. Those manifests are pointing to the physical files in object store in S3, and that's where you write those files, right? And everything here, as you can see, is inside of an object store.